Okay, so we'll start, part 3 of this series. And to do that, I am going to start this time with just a simple Rhino object here. I'm just going to go over to my front view and draw a surface plane that we can use to get rolling. So I'm just going to go to surface plane, corner to corner, and just drag out a surface, something like that, I guess. Yeah, that'll do. And I'll turn that into my shaded viewport here so I can see it. And I'll bring that along for the ride into Grasshopper. Okay, so I'll head over to the parameters, grab that surface parameter there, and set that surface in so we could now go ahead and use it. And for the meantime, I'm going to hide that. I don't need it just yet, but I won't internalize or delete because I'll make some changes to it later. Okay, so we have a surface from Rhino set into Grasshopper currently. So let's subdivide this thing. What we're going to end up doing is breaking this thing down into smaller parts so that we can add, let's say, a bunch of panels to it, maybe for a facade, maybe for a sun shading, maybe just for the kind of the general exercise of populating a surface with three-dimensional objects. So we have to break it down into smaller things, smaller surfaces. So it's just a basic kind of subdivision routine. So let's head over into our Surface tab here, and over in Utilities on the right you'll find ISO Trim. And what this is going to require is both a surface input and a domain. It's going to need to know how many times we want to break the surface down in both the U and V directions. So for a little bit more on the U's and V's, I certainly recommend heading into our course kind of primary reference, which is the primer that's set up for you on the Miro board. But I'll kind of speak just more generally about the U's and V's. Basically, the locations in one direction and the other on a three-dimensional object. So it's basically, think about it like the X's and the Y's of a surface, if you will. And that is a gross oversimplification, but I think for the time being it's useful. Now, so let's find the proper domain component for this. We can go over to the Math tab here and go all the way down on the left side here on the domain. You'll find all the way at the bottom here that divide domain squared. This is going to be the one that we'll use to basically inform this component in terms of how many overall times we want to break the surface down in both the vertical and the horizontal direction. And that's going to be set by the U and V value coming in as a number. So by default it's set to 10 and 10. If I plug that in, you'll start seeing some overlapping previews. So go ahead and turn off that preview for the original surface, and you'll just see what looks like a grid that's been drawn over our original. But actually, if you look at the output of this component, it's 100 trimmed surfaces. So there's 100 small little rectangle surfaces that are now organized as they kind of rest along that original. And why is it 100? It's because the U and V values here are set to 10 and 10, so it's a multiplier of that. Okay, so I'm going to go ahead and make a couple sliders between 1 and, let's say, 50. And as I plug that one in, you can see that I'm bringing it down only one time, which is basically one big surface in the horizontal direction, but 10 times vertically, because that's still set to the default. 1 to 1 is, of course, just going to give us the original surface without any subdivision. But as I increase these values, you can see that now I'm breaking it down. For the sake of this, I don't know, I've got something set maybe to like, maybe 20. Yeah, we'll start with 25 and 15 for the time being, although, yeah, maybe something less, 25 and 10. I kind of want these to be sort of vertical rectangles. All right, and you can have something a little bit different on your screen. It really doesn't matter that much, but that's what I'm going to start with. Okay, so here we go. So let's check this out. So from a single item, we ended up with 100 different items. Or sorry, in this case, 250 because I changed the values from 25 to 10. All right, so here we have a list of multiple things and a single list coming in as an input. Let's take it one step further and build a simple data tree by extracting some information out of these. So I'm going to go to Surface Analysis, and this one here looks like a flaming cylinder, the Deconstruct BREP component. I'm going to plug that in, and then I'm going to turn off the preview for the previous step here. All right. So now all I'm left with is the outputs of this component here, which is going to be our faces. That's going to be our individual surfaces. And you can see that there's a data tree that's been drawn here, that's been set up. So basically I have 250 lists of one item each, and that's fine. You know, that's basically just each individual surface has been kind of placed into its own list. But here's where it gets a little bit more interesting. We've got now, we know that every surface we can extract 4 edges. So here's where the data tree becomes quite useful. On the left, you can see each one of the surface locations, basically. So we have 250 surfaces, so we should have 250 lists. Each one of those lists has 4 items, because each one of the surfaces can have 4 edges. So that's what the end value is there, is basically the number of edges listed out individually as data output. So we can select those individually if we'd like. The other thing is the vertices is going to be similar. So a square has got 4 corner points. So the points you're seeing are actually overlaps, you know, similar, I guess, to the grid components, if you look at the grid cells. But here we've got 4 vertices per surface, 4 edges per surface, and then the surfaces themselves. What I like to do with this component oftentimes is I like to bring out the outputs separately, because then I can turn this component off and view them one thing at a time. So just making sure you're kind of matching the geometry types with the component inputs, right? So surfaces go into there, curves go into curve, and then or I should say edges go into a curve input, and the vertices to a point input. And now I can kind of, you know, determine what I want to see and when, without having to see them all at once. All right, so it's kind of useful, you know, just a little something there. Okay, now what can we do with this? You know, you can think about this now as the starting point from which we can start to draw a huge amount of things, right? So we've got 4 points. Basically, anything you can draw in 2D with 4 points and a surface, because we can always find a center, and maybe even thinking about using the 4 edges. You know, what kinds of things can you come up with? There's a huge number of things you can design into that as a base collection of items. I'm going to start with the vertices. I won't use the other things just yet. Just going to use the vertices for now. Now, let's say, for example, I wanted to draw a diagonal, and I'm going to turn these on just for a little bit better preview. Let's say I wanted to draw a diagonal line and basically convert this setup into a diagrid. I would need to know which points to connect within each one of these rectangles to draw diagonally across. But this is all 4 of them. So I have to be able to extract the 4, pick the 2 that I like in order to draw the diagonal, and then create the line. So let's go to Sets, List, and List Item. And then kind of referring a little bit to what I was talking about in the last tutorial, I can zoom in on this, I can hit this a few times, but only so that I have 4 outputs, because that's as many items that I have per list, right? N equals 4, so I should have 4 outputs here, which is basically 0, 1, 2, and 3. So that's going to allow me to select those points independently as inputs to a new component. So I'll go to Curve and Primitive and Line, and then I'll just kind of skip. So I'll start with 0 and skip down to 2 and draw the line. That's going to give me, based on the order of the points, in this case it looks like it's counterclockwise, my diagonal. If I want the opposite diagonal, I can simply just plug in 1 and 3. I'm going to turn these off, and that one, just to kind of show you how we can kind of go back and forth. Right, so there's one, and there's the other diagonal. But if I turn them both on, and if I turn off my surfaces, basically the net effect of that overall is sort of a diagrid pattern, you know, diagrid structure, if you will. So if I select, and if I wanted to make those lines continuous, I can just simply join them out of this output, because even though that they're separated into different segments, basically what I can do is flatten this output and join them together, and the join command is only going to join curves that are touching one another, at least at a connected end or start point. Okay, so if I wanted these to be like long, continuous members in a digrid structure like a lattice, I could do that. This would be a relatively easy way to do that, just by joining them together. All right, so just to take a look at that, I could just show you, so flattening that and then joining will produce 34 curves in this case. Yeah, they're continuous. All right, but that's not what we're here to do, but it is just a simple example for how to manipulate, surface subdivisions into a new kind of structure. Okay, another thing that I think we should check out basically is, I guess I'll start just with one of these. I guess I'll work with those. I'll turn those off. But let's say we wanted to add some variety to a panelization, a surface panelization, or maybe it's some sun shading, or maybe it's just different openings. Just to kind of put it in really basic and kind of dumb architectural terms. One thing I'll do is I'll kind of reintroduce that curve evaluate component, right? So evaluate curve, I'll head back over to curve under analysis, you'll see that there, down here toward the bottom and then on the right. And I'll plug that in, and then I just need a slider to draw a point along that line. Alright, and you can see that at 0 it's down at the base, the starting point, and then I can move those up, accordingly. So this might be a way to start developing a repeatable pattern, because now what we can do is draw another set of lines to that center from the other corners. So maybe that instead of this, we can use this as a new point to draw new lines that go from the opposite corners of these to that point in space. So let's go ahead and grab a curve component, and then I'll just go ahead and the points that I'm not using here, so it's going to be 1. In fact, I'll delete that to clarify. And then this output will draw my first segment. I'll copy and paste that, and then I'll just plug in the 3 in place of the number 1 there. Sorry, the A input. Alright, so I'll just kind of leave that up on screen for a second, so you can pause if you need to, just to see how that's constructed. But now we get a kind of an interesting sort of tiling that's developing here. You can almost look at it like a shingling, maybe. You can think about it in a number of ways, but you can change it. Right? You can go from its digrid form to its diagonal and back again. That's quite nice. And we can turn those points off to see maybe even a little bit better. So we're working, within a really simple kind of parameter set here. It's just a square, but the overall effect of it gives us, quite a bit to work with here. It's kind of there's quite a good variety that's implied. That said, it might be fun to just kind of play with replacing this slider with a range of values, kind of like what we were doing before. You might think, well, maybe I could input a attractor point here, which is true. You might also just kind of use the graph mapper to just start to prototype different kind of varieties coming across the surface. So maybe we can do that, and then we can take a short breather, and I'll head into the next video. So let's grab a graph mapper. We'll go to parameters, graph mapper here. All right. We do need a range of values to input into this. So what we're going to do is figure out how many points we have, or lines, whichever. So I'm going to do that. I'm going to go to set and list length, plug that in, but then I have to flatten that input, right? Because I just want to count how many overall items I have, not many lists, not as many lists. So there I have 250 items. I'm going to stay in the set, and I'm going to go to sequence and go to range. Right? This is going to set us up with a nice range of values using this as an input, but keep in mind that, again, this is going to always output one extra thing. So if the number of steps here is 250, that's between 0 and 1, so it's going to add 1 extra. So basically what we want to do is put a little expression on that. You can just kind of right-click on that N input, go to expression, and just say x minus 1. All right. Otherwise, we get 1 extra data point that we don't need here. So now I have 250 numbers between 0 and 1 that I can plug into the graph mapper and kind of make some changes to, kind of massage that between massage those values between those bounds. So I'm going to change this to, I don't know, let's just say the Bezier for now. And I'm going to go ahead and so here's where we got to kind of take a pause here, all right? Before I start connecting stuff, let's take a look at what we've got data-wise. I had to flatten this because I needed to know how many items, just overall how big this range of values needed to be. Now the output of that, of course, is going to be a single list of multiple items, but the structure that I want to compare that to is not that. So I have two options here. If I plug this in, well, I have three. The third one actually though is going to be an error. So if I plug this in, I'm going to end up with a lot more things than I need, right? It's going to get pretty red, and I don't think this will crash, so I'm just going to go ahead and do it. All right, so that's insane, right? So it's basically showing us every single possible permutation by basically connecting every one of these lists independently to all 250 options within each square, right? So that's basically just going to paint the town red. So let's disconnect that. I don't recommend doing that if your computer's kind of slow. That might have bogged you down a bit. I could either graft this, I can create basically the same data structure, so make it match again, or I could simply just flatten this one. Knowing what to do depends on what your next steps are. And sometimes it doesn't matter, sometimes it does. In this case, I'm going to opt to graft the output here so that my output coming out of the graph mapper matches, and I can test this real quick just by using a panel if I like. Well, sorry, not a panel, but if you want to go to Utilities, Parameter Viewer, this will tell you basically what you've got coming out from each of the two things that you intend to match. And you can see they're identical. Data with 250, data with 250, n equals 1, n equals 1. So that's pretty good. That's comfortable. So now I can go ahead and place that, and everything is happy. You can now see then that I have a variety. My variation coming out of the range here is producing a pretty nice effect, isn't it? This pretty beautiful transition from a diagonal line to basically a diagrid, and then back to a diagonal in a square. Now, of course, making changes to the graph mapper will make adjustments to the overall pattern. Okay, so this is a nice way of kind of tie back to some of the stuff we did before. Going to linear, keeping that as it is, playing maybe around with something that comes back around. So where is it? The parabolic might be nice because basically it comes, if you were to wrap this around a cylinder, it would come back around and match as a continuous pattern. For now, I'll leave it on linear because I actually kind of like how that looks. Okay. Now, last thing, is just to take a peek at, and remembering that we drew this along a surface in Rhino, and so what was the point of that? That's going to be in the next step, but let's just go ahead and show it. All right. Get rid of some of these older things here from previous steps, and now if I turn on the gumball here, I can just rotate this, and you can see that basically we're recreating that drawing along the surface in any orientation, because we have yet to add three-dimensional input, but also because the entire grasshopper work is all contingent on this surface regardless of its location in space. All right, so regardless of whether or not you have tilted planes or straight planes, the result is the same. Okay, so let's leave it at that for now, and we'll use this as a starting point to part 4.